Hi, I am back again to talk to you more about moles and gases. Last time we met like this, we talked about gases when they were at STP. You should recognize this paper. This is what I filled out in the last video. And the purpose of STP, remember that it stands for standard temperature and pressure. These are conditions that like a scientist would hold a gas at in the lab. We want to keep them in this specific condition in order to be able to compare it to other gases. The thing about gases is that when you change like one condition, like the temperature, or you change the pressure, it greatly varies the volume of the gas. And so that's why they have that like standard amount that they hold things at to do comparisons, like things like density and stuff like that. And what we learned about in that last video was that at STP, any gas, right? Any gas has a specific volume. 1 mole has a specific volume. So 1 mole of any gas is equal to 22.4 liters if it's kept at these very specific conditions. So again, standard temperature and pressure. The standard temperature is equivalent to 0 degrees Celsius, which is like the freezing point of water, right? So really super cold. And I know like our classroom feels it's real cold most days, but it's not that cold. And then pressure is 1 atmosphere. And we in Colorado are much lower than 1 atmosphere, because we're higher up and all that fun stuff. So this is true if you are at STP, and you should have practiced at this point how to solve problems. It's just a conversion fact. It's similar to using the mass conversion, not a big deal. What I want to talk about with you now is when you have a gas that's not at STP. So as you know, last week in class, we did a lab with, the inflatamole lab, and we talked about the mole at STP, but in reality, like I mentioned, we weren't really at STP. Our classroom was not at 0 degrees Celsius. It was probably more like about 20 degrees Celsius maybe. And the pressure in Colorado, I think usually comes out right around 0.9 atmospheres, although with the weather and stuff, it could have been a little bit lower or higher. So, but not standard temperature and pressure. So how do we handle that? So if you take this paper that you got from me in class and you turn it over, we're now going to talk about gases when they're not at STP. So when gases are not at STP, then you're going to use something called the ideal gas law. We're going to use the ideal gas law. And what's funny about the ideal gas law is that technically nothing is ever ideal. And technically, the rules of the math don't really apply, but that's way complicated chemistry that you don't need to worry about, okay? So we're going to use the ideal gas law anytime we're talking about a gas that's not at standard temperature and pressure. And so like you can see in this first problem right here, it talks about having a volume of 35.5 liters, but the pressure is 0.9 atmospheres and the temperature is 100 degrees Celsius. So what do we do in that case? 1 mole is equal to 22.4 liters is no longer true. So how do we solve that? Okay. So the ideal gas law takes pressure, volume, and temperature and combines them together to give us moles. And it also has a constant in there in order for it to be true. So the ideal gas law looks like this. It's pressure times volume is equal to the number of moles times a constant, don't worry, we'll label all of this, times temperature. So just a nice, simple little algebraic equation, nothing too bad. What I want to do is go through and label what each of these variables mean. Again, as I mentioned, P is pressure. And pressure can actually be measured in several different units. There's atmospheres, which I had mentioned already. There's also kilopascals. Like if you have any friends in honors chemistry, they use kilopascals a lot. The pressure that we measure like our weather in is millimeters of mercury. But we're going to focus, and I'm only going to ever give you problems when pressure is at atmospheres. And we'll talk in a second about why it's important that we're clarifying that that's the unit for pressure. V is the unit for volume. And again, remember, the reason we're talking about volume right now is because gases are very, very small and they take up a huge amount of space, which makes them difficult to mass. So we had to come up with a different way to measure them so that we could count them. And so that's how we got to volume. Volume in this case is liters. Okay, then you have N. And, this is just one of those crazy chemistry things again. N represents moles. And a lot of people are like, why can't M represent moles? Well, the lowercase m is actually used in physics to represent small masses. And since the two subjects work together so much, we couldn't use the same letter to represent things. So that's how we got to N. Remember too, for moles, that you can convert from grams to moles. So if you ever have a problem and they give you the grams and you need moles, that's an easy enough conversion to do, right? So it's in moles. And then also we have temperature. That's what the T stands for, is temperature. And this might be kind of a new idea to you. Temperature must be in a unit called kelvins. And you've probably never necessarily heard about them before, but when they first started working on gas laws, one thing that became very apparent, and you probably know if you've ever like sprayed yourself with hairspray or spray paint or something, that gases can get very cold. Their temperature can drop below zero, so into a negative value. If we were to take a negative value and plug it into this equation, it would give us other negative variables, like a negative volume or a negative pressure or a negative number of moles, which you can't have, right? So the scientists who developed these ideas said, you know what, we need a temperature scale specifically for gases that doesn't ever go negative. So basically they figured out experimentally, it's not even actually ever been reached, the very, very coldest possible temperature. It's called absolute zero. It's a theoretical value. It's equal to negative 273.15 degrees Celsius. They figured it out, just did some math and drew a graph basically and figured out where it was. And then what they said is like, okay, so if that's the coldest possible temperature, we're going to make that zero on our Kelvin scale. So nothing can go below that. So the thing is we don't have thermometers in our classroom that measure in kelvins. Our thermometers measure in Celsius, right? So anytime we're given a temperature, it's always in the unit that we're used to working with, and you have to convert it to Kelvin, which is easy enough to do. All you do is take the Celsius and add 273, right? So when we do gases, they always have to be in Kelvin, and it's easy to do. Just add 273. Okay, then the last variable that we have there is R, and R is the ideal gas law constant. And you have heard of constants before, like pi and things like that, right? You always have to use the same number. Same thing is true here. In order for this equation to work out, we have to have this constant value. And the value of this constant changes based on the units that you use. So remember a minute ago when I was talking about how if you use a different value or a different unit for pressure than atmospheres, then that would change the R that you use. In this class, especially this year, we're only going to ever use those specific units. I'm not going to make you ever change them. So the value of R is always going to be 0.08206. Kind of an annoying number. You don't want to leave off any of those decimals or it could mess things up for you. This number does have units, and the units are atmospheres and Kelvin and volume and moles. We're not going to worry about them. It just complicates things by putting them in, but it has a unit so that whenever you plug it into this algebraic equation, it'll cancel out the other units so that you can get whatever you're trying to solve for. Okay, so this is the ideal gas law. You just plug in your numbers from your problem and you solve for whatever you're looking for. Now, I want to make your life as easy as possible in solving these problems. And in this particular unit, we are only focused on moles and solving for moles, right? And counting by measuring using volume or grams. So we're only going to be either solving for the N, the moles, or we're going to be solving for the V. So what I want to do right now is rewrite this equation, solving for just volume and then also solving for just moles to sort of speed up the process for you on solving these problems. And then we'll do a couple of example ones together. Okay. So if I wanted to say solve for moles, right? We know in algebra that in order to solve for a particular variable, you have to get it alone. So you'd have to take these two numbers over here and divide by them. And then, of course, math is fair. So if we divided by those two numbers on this side of the equation, we would need to then divide by them over on this side of the equation. Okay, so long story short, if we rewrite that equation to solve for moles, it would look like this. N is equal to the pressure times the volume divided by the constant times the temperature. So that's how we do this problem for moles, to solve for moles. And you would use this equation when you had pressure, volume, and temperature. Now, if you are doing calculations and you already have moles and looking for volume, then we have to rewrite the equation a different way. In that case, we're trying to solve for this V. We need to get it by itself. So we're going to take the P, divide by the P. If we divide by pressure on this side, then we have to divide by pressure on this side. So to solve for volume, and again, remember volume will be in liters. You're going to take that ideal gas law and manipulate it around so that you're going to take the number of moles times the constant times temperature and divide by pressure. So again, these two equations are just the original ideal gas law rewritten to sort of make your life a little bit easier. So when you do these problems, you have to figure out, what am I solving for? Am I solving for moles? Or am I solving for volume? And then pick the right version of the equation to use. So let's check out number 5. And again, remember, it's numbered weird because of the other side of the paper, right? We did those last week. Okay, so number 5 says how many moles? So I'm looking for moles. So my N is my unknown of chlorine gas would occupy a volume of 35.5 liters. So I'm just going to write a V above that because that's my volume. And a pressure at 0.9 atmospheres. Again, it tells me that's the pressure. So I'm going to write a P on there. I love labeling my problems. Just keeps everything nice and clear. And then at a temperature of 100 degrees Celsius. Now remember, temperature always must be in Kelvin. So we need to take that temperature and add 273 to it to get 373 Kelvin. You have to have it in that temperature or in that unit in order to use it in this particular equation. All right, so we are looking for moles, right? It was right by the question word, how many moles? So that means we're going to want to use this version of the ideal gas law. So we're just going to take that and I'm going to rewrite it right here just for ease. Okay, so I can move my paper up a little bit. But now what we're going to do is we're going to plug in the numbers that we have. So again, N is equal to the pressure. So pressure is 0.98 atmospheres times the volume. Volume is 35.5 liters divided by R. And again, remember, the R is that constant value that we have there, just like pi. 0.08206, and then also divided by temperature. And we calculated that our temperature was 373 Kelvin. Okay. Just to clarify really quick before I solve this problem, this that I wrote on the paper is the minimum amount of work that you must put down for full credit. You don't have to show any of the other calculations or anything like that. You don't need to write this out. You don't even necessarily have to show that. But in order to get credit to show your work, you need to write it out in this manner so that I can see what you're doing with your numbers. Okay. Then we're going to plug that into our calculator. So we're going to start with the numbers on the top. And as you hopefully know, we, of course, are going to multiply, right, by everything on the top, multiply by the top. And then, so let's see here, that will be 0.98 times 35.5, right? So we're going to multiply by the top, and then of course, we divide by everything on the bottom. And this is always what gets people, is because they see those two numbers written next to each other. So they hit divide once by this number and then they hit times, right? That would only be true if you put them in parentheses. So I just like to do it. I know that anytime I have a number on the bottom, I just always need to divide by them. So I'm going to hit divide 0.08206, and then I'm going to hit divide again, 373, right? Because again, both numbers are on the bottom, so we have to divide by them. And we get 1.1, remember we're going to round to 2 decimals, 1.14, and what were we solving for? N, which is moles. Okay? Very, very basic plug and chug algebra. Shouldn't be too much of a problem. I tried to be really careful about labeling the problems. As long as you know that pressure is atmospheres, right, and volume is liters, and temperature is Kelvin, even if the problem doesn't explicitly state that the present pressure is such and such, if you see that unit, you would know that that's pressure. Okay? All right, let's look at another example. So let's look at number 6. It says, what is the volume, right? So I am looking for volume of a balloon if it contains 3.2 moles of helium at a temperature of 20 degrees Celsius and 1.02 atmospheres. Now, one thing really quick I want to point out, this problem and really the previous problem both mentioned the specific gas that you were dealing with, but did you see anywhere that the identity actually mattered? This problem could have easily have been about helium, and this problem could easily be about chlorine. When we're solving for these, just like with the ideal gas or with the STP situation, the rule is true for any gas. It doesn't matter what the identity of the gas is. Okay. So let's decide which version of the equation we want to use here for this problem, right? There's to solve for moles here or to solve for volume. And again, it says what volume, so that's what we're looking for. So we're going to use this version of the ideal gas law. And again, I'm going to rewrite it just for making it easier to look like. So V is equal to nRT over P. And then I'm simply going to plug in my numbers and chug it through my calculator. Okay, so I'm going to say that V is going to be equal to N. So our number of moles, remember N is moles. So that's my N, right? Temperature, here, let's do this. It's 3.2 moles. R, of course, is 0.08206. Temperature, remember, must be in Kelvin. So I was given 20 degrees Celsius, so I need to take 20 plus 273 to get me 293 Kelvin. That's my temperature. Right? And then I'm going to divide by the pressure. And again, pressure is always measured in atmospheres, so I know that the pressure is 1.02 atmospheres. Okay. So I plug all those numbers now into my calculator. So I'm going to do 3.2 times 0.08206 times 293 divided by 1.02, and I get 75.43. And again, we're solving for volume. What's the unit on volume? Remember back up here? Volume is always liters. So I got 75.43 liters. Okay? So there's one version where we're solving for moles and one version where we're solving for liters. All right, let's look at this next problem. It says, what volume, so again, I'm looking for volume, would 20 grams of carbon dioxide occupy? So tricky situation here. It mentions mass. Is mass mentioned anywhere in the ideal gas law? The answer is no, right? But can't we convert mass to moles using the molar mass, right? We can. So I'm just going to add that up here. Or you can convert grams to moles. So if you're given grams in a problem, we're going to have to convert that to moles. So real quick, I'm going to do that. I'm going to take 20 grams of carbon dioxide. Of course, in order to convert from grams of carbon dioxide to moles of carbon dioxide, I have to know the molar mass. I do that by adding together 1 carbon and 2 oxygens. So I get 44.01 grams. So I know that 1 mole is equal to 44.01 grams. That should all be a huge review for you because hopefully you guys have completed mole calculations number 1 and 2. So we're going to do 20 divided by 44.01, and we get 0.45 moles. And of course, that's my N, right? So I have N. Then it says it has a temperature of 25 degrees Celsius. Again, remember that temperature has to be in Kelvin. So we're going to take the 25 and add 273 Kelvin. here, I guess I should write what it equals. Oh, my eraser is out of there. So this would equal 298 Kelvin. And then 1.04 atmospheres, of course, is pressure. All right, so we have all our variables labeled. We are looking for volume because it explicitly says what volume. So we look up here. We're going to take our ideal gas law and we're going to solve for volume. So this is the equation that we're going to use. So let's plug all of our numbers in. So volume is equal to moles, right? Here you can see it up in this previous problem. We just figured out that the moles for this problem are 0.45 times R, which is 0.08206, times temperature, which is 298. And then we're going to divide the whole thing by the pressure, right? Pressure goes on the bottom, which is 1.04. Okay, remember this is the minimum amount of work that you need to put down on your paper to get full credit. That's all you have to do. You don't have to show me anything else. You put down that information, and then, of course, you would plug the rest into your calculator. So we're going to do 0.45 times 0.08206 times 298 divided by 1.04, and we get 10.58. And again, we solve for volume. The unit on volume is liters. Okay. All right, let's talk about number 8 here. It says, what mass of nitrous oxide gas? So we're looking for grams. Okay, again, let's go back up here and look at the ideal gas law. Is there anywhere in the ideal gas law that you can explicitly solve for grams? No, right? But can't we convert moles to grams? We sure can. So in this problem, we are going to solve for moles. We're going to solve for moles. Solve for N. And then we're going to convert to grams. Okay. So let's look at what other information we have. We want to know what mass of nitrous oxide gas is contained in 20 liters. So that's my volume. So ultimately, I want to know how much this volume of gas weighs. At a pressure of 1.2 atmospheres, that's my pressure, and a temperature of 25 degrees Celsius. Again, remember, we have to convert that to Kelvin by adding 273. So I'll do 25 plus 273. Just like in the previous problem, that'll give us 298 Kelvin. Okay, so we are solving for N to start. So let's look back up here at our equations. We're going to take the ideal gas law and we're going to solve for moles. So we're going to use this version of that, right? Again, this is just this equation rewritten to solve for moles. So we're going to take N is equal to, I'm going to rewrite it here just because I don't want to get confused. N is equal to PV over RT. So the pressure is 1.2 atmospheres. The volume is 20 liters. R is that constant 0.08206. And temperature we calculated was at 298 Kelvin. Okay. So again, we multiply by the numbers on the top and we divide by the numbers on the bottom. Let's clear this out of here. So we're going to do 1.2 times 20 divided by 0.08206. And then we also need to divide by 298. And we get 0.98 moles. Right? But remember, we're not trying to solve for moles of N2O. We're trying to solve for grams. So this was step 1. Step 2 is to convert that to grams. In order to do that, we have to know the molar mass of N2O. We have to know what the value of 1 mole of N2O is. Well, we can figure that out pretty easily, right? We just add together 2 nitrogens, which are both 14, to give us 28, plus 16, right? So 28 plus 16. Whoa, not times, sorry. 28 plus 16 is 44. This one's also 44. Okay, so we're going to take that conversion fact And we're going to multiply it by the moles so that we can convert from moles to grams. So I'm going to put the 1 mole on the bottom and the 44 grams on the top. And then, of course, we'll multiply across the top and divide by the bottom. So 0.98 times 44 divided by 1. The answer that we're looking for is 43.12 grams. Okay, so a nice and easy two-step problem. Simply plug and chug your numbers in. Really, all it's going to require on your part is just doing a little bit of practice. And that's what I have for you next, is you have another set of mole calculations to do. Okay, let me know if you need any help. Thanks.